Namaskar, welcome back. So this was the last slide where we were discussing, and as I told that now we will quickly take up the trenches and the paleoseismic studies that we did in India uh, in the Himalayan zone. Now, one important point which I would like to mention here is that as we have been learning that we will do one is the field investigations or field mapping, and then followed by that we will do paleoseismic investigation. So, paleoseismic studies. So, what is important here is that one has to look at the topographic signatures. Okay. So, you see for the topographic signatures as well as then further the stratigraphic records in trench. Okay. So, topographic signature helps you in understanding that whether the scarp is cumulative scarp indicative of multiple events or not, and similarly that goes for the sedimentary records or the stratigraphic records in the trench. Okay. So, they opened up the trenches across the most recent scarp which was formed, and of course they were also able to observe and during the Alasnam earthquake that the scarp was much higher, and that was related to your multiple events. Okay. So, if you see the trench, that clearly indicates that there is the older units which are sitting down have been displaced more as compared to the younger units. Okay. And this is the fault trace which goes over here, and then finally it has been capped here at by this unit here. Okay. So, if we look at unit C, then unit C has been displaced maximum actually, and along with that you also see that this is another unit which has been displaced more as compared to that. So, that indicates that clearly. So, this will go up to, like, you can, if you take the net slip, then this will go up to this point here. So, this is the top here, and then this will be the net slip of that. Okay. Whereas the net slip of this unit will be somewhere over here. Okay. So, unit C has been displaced more as compared to the another upper unit capping unit C. Okay. So, this is how they have explained that how many events would have occurred during this earthquake. That more than 3 events have been recorded, and the fourth one was your 1980 event. Okay. So, mostly what we do is that we go for retrodeformation after identifying the similar units if we come across on both the walls or on either side of the fault, then we try to compare that and then do the retrodeformation. Okay. So, for example, A1 or this is 1 here which they have given. So, they say that the scarp existed before the event which they identified in their trench, and then there was another event which resulted into the displacement of. So, or we can say that event 1 here, okay, which was after this unit. It's not very clear, but if I say, then this probably is the unit E, if I am not wrong, then that what they say that. Okay. So, if you see this top blackish unit was faulted, and then there was a deposition of this unit over here. Okay. So, this is the post deposition, and then there was a displacement of the event, but before that there were few more layers which got deposited. Okay. So, looking to the events here, you can like looking to the displacement of the units, you can identify that how many events have occurred. Okay. Now, straight away going to the Indian part, as we have already discussed that why this area is important in terms of the seismic hazard assessment, because we have multiple earthquakes which were been observed during the historic time. Okay, but we don't have the records of older than like 12th century or so in this area. So this part also we have discussed that we have multiple fault systems, MCT, MBT and HFT, and HFT or MFT is the most active in the frontal fault. Okay. So if you look at the area, so this was the project which we did for Ministry of Earth Science. The background behind this was that the objective was to identify the active fault traces and to do paleoseismic investigation wherever applicable. Okay, we were not able to completely do the paleoseismic investigation of the hinterland fault site, but mostly we tried that few hinterland faults along with the frontal faults were been covered, and we were able to do the paleoseismic investigation in this area. Okay. So, idea behind this is again to prepare a digital active fault map, and hopefully in couple of months we will be publishing an active fault atlas. That will be the first active fault atlas in India from Himalayan region. Now, coming to the northwest Himalaya, of course, uh, which is of the overall Himalayan terrain is a very dynamic terrain. Okay, but let's see this part here, and this is a part of the tectonic geomorphology. But yes, of course, the uh, tectonic activities have very prominent manifestation on the surface, which can be interpreted based on the geomorphology or the morphology of the surfaces. Okay. So, here in this area, the yellow epsilon which has been marked on the figure, it shows the January anticline, and this January anticline was not what we see today. Okay. So, the story goes as follows, that uh, if we consider that these two folds, okay, or the anticlines, okay, that is, one is your Chandigarh anticline. So, this is your Chandigarh anticline, and this one is your Janauri anticline. Okay. So, what we observed was quite interesting, that in the central part, or maybe you can say in the some portion of the Janauri anticline, the area was quite flat. Okay, and that was been interpreted based on the drainage density was less over there and all that. Okay. So, that what we interpreted, that this is the area of uh, fault. So, this is the area of fault linkage, which where two faults, along with that the folds, okay, interacted and resulted into this uplift. Okay. So, that was the concept which was been given. So, before this there was an interaction. We'll come to the process how it happens actually. So, before that, this area was, like we can say, a sort of a gap through which the Shatluj flowed. Okay. And that how we also identified the paleo channel of this area. Okay. So, coming to this, the concept behind this and the theory, or we can say the segment linkage model, if we take, then this is well explained by Cartwright and then by Davies and all that, and this is most common in the fold and thrust belts. Okay, where the folds and related faults will laterally propagate and get linked to result into the formation of the larger anticlines. Okay. So, this explains the fault growth by segment linkage. Okay. So, the fold uh, will grow radial with the radial propagation, and this is the plan view which has been shown, and this side what you see is the sectional view. Okay. So, if we say that there are different segments, and fault also develops or move in different segments. Okay. So, you have three segments here. So, slowly what will happen that there will be in growth. So, there will be it will start with the nuclei, then it will propagate on either side. Okay. And that will keep growing. Okay. So, for example, in this will grow further like this. Okay. Or you can say that it keeps growing like this, and the next further it will grow further up. Okay. So, this growth, so this was during one and then further propagation in total here, and if this growth is ongoing, so it will try to interact with the other uh, folding and fault lateral propagation of the faults which is developing. Okay. So, maybe time will come when these two sections will interact. Okay. So, this is the linkage point. Okay, between the two folds, and that is how the things grows, and finally you will end up in getting a larger fold or the anticline, but which was developed because of the linkage. Okay. So, these are the point where the two segments interacted. Okay. And final topography which you see is will be something like this, and this will be your the linkage points. Okay. So, exactly this process we tried to understand and implied to the formation of your Janouri anticline. Okay. There is another model which was been given by Davis, which also talks about the segment linkage, and the movement or the displacement will start at a nucleation point and then it will laterally propagate. Okay. And so, lateral propagation as well as the elevation also will be gained. Okay. So, and this has been given by Davis, okay, who also talks about the similar process and the linkage of the segments. Okay. So, before the linkage, you can say that there may be a drainage which would have flowed through this one. Okay. But later on it would have blocked and then forced to move somewhere like this, or it might have flown like this. Okay. So, behind the eggshell portion of the fold. Okay. And this is exactly what we saw in Janouri anticline, and we were able to also pick up the paleo channel of BS. So, this was the paleo channel of BS which flowed through this line over here. Okay. But after the linkage of these two segments, okay, so one segment is this one here. So, you have this segment here, which, and then another one is this one. Okay. So, after the linkage of this segment and a sort of an higher rate of uplift, okay, in the linkage area, that disrupted the bias channel and forced the Shatla channel and forced the Shatlaj to flow through its present path over here. Okay. But the earlier flow was this one. Now, there is one research group has already worked on this, and they have given the timeline for this, when was the last uh, uh, time the Shatluj flowed through this area actually. So, this is what we have tried to explain based on the schematic diagrams, that initially there was no Himalayan frontal thrust, but which was Nahan thrust was there, and the frontal portion was like similar like what we see in Gangetic plain. Okay. And Shatluj flowed through this region without any hindrance. Okay. But later there was growth of this fault, new fault came up, that is Himalayan frontal thrust, and that resulted into the uh, lateral propagation and also development of the fold moving in either direction laterally, okay, along the strike. So, until they did not interact, they, it allowed the Shatluj to flow through. Okay. And then finally, it blocked the Shatluj. Okay. So, Shatluj channel was, we can say, disrupted because of the upliftment in the central portion. Okay. So, as I told that this lateral propagation of the fold related folding is most common in thrust and fold belts. Okay. So, this is not just the one example we see, but this similar examples have been observed in other part of the world also. Okay. And even along the Himalayan zone, we see similar type of examples from number of places. Okay. So, this is what we have, the interaction of that of the, now what we are having is the two ends of the fold here, and on the northwestern portion over here, again there is a clear cut example of the propagation of the fold and the shifting of the Bias river here. Okay. So, this was the Satluj paleo drainage. Okay. And then finally, the Shatluj started flowing through this area. Coming to this part, as I told that this is again another example of lateral propagation of the fold and related folding, where we have a typical plunging fold over here, which will keep growing further, and as the events comes, this the bias will be forced to flow through this actually. Okay. And this has happened in the past. Okay. So, you have a sort of an lateral propagation of the fold. Okay. And so, as I told that not only in India or in the Himalayan zone, but this type of examples are also seen, or evidence are also seen from other part of the world. Okay. So, this is an example of Wheeler Ridge, where similar process was involved, which resulted into the shifting of the channel. Okay. And leaving behind the paleo wind gaps. Okay. So, and that is what they have also termed as water gaps. Okay. Or wind gaps. Okay. So, propagation is in this direction. Now, one important part which you should remember is that as you move in the direction of propagation, okay, because then you will be able to see that topography reduces. Okay. So, if you take the profile, then what you will come up, you will see is that in the direction of propagation, the topography will reduce. Okay. And topography will be higher in the central part or the other direction. Okay, opposite direction, but the propagation is in this direction. That will also say a reduction in topography. So, this is the same example what we were discussing about the your Shatluj and the Bias. It flowed through this one before the propagation. Then there was a propagation of the fault and related folding, and then it allowed uh, or force the channel to shift and take the newer path, and then finally what we see, the propagation was in this direction further, and at present we see the bias flowing through, has occupied its current position. Okay. And in future, of course, this will also propagate further, which will result into the shifting of the bias channel. Now, there is very interesting story in this area, which we will discuss, because we did trenching in this, and then we have done a lot of paleoseismic investigation along this. So, if you carefully look at the shape of this uh, fold, then it is like a tongue shape. Okay, over here. This is the portion which is in 2D. It looks like that it is a flat area, but it is not flat. There is an elevated portion. Okay, and there are number of faults. One fault goes like here, and this is the fault which moved during the most recent event. The another fault which is along the front is goes up to this one. Okay, we were able to see, and further, as I told, that the your elevation reduces if you move in this direction. Okay, and that is the direction of propagation. So propagate the fold propagate in this this direction. So we open up trenches over here in this area, and even we have opened the trenches over here. Okay, in this area as well. So I'll show a couple of trenches which we have done in from this region, and then we will move ahead. Okay. So this is the close up of that we have. Okay. The if and if you try to look at my, I'll just put my cursor here, then this is the line over, this is the portion of the active fault. Okay, so this goes like this. Okay, so maybe I can put the line here then. Okay. So this is the trace of the fault. Okay, so this side is up, this is down, and then again you have the trace which goes over here, and this goes up to this. This side is up relative, and this side is down. So this is your endogangetic plane. Of course, the whole portion is the part of the endogangetic plane, but this portion has been uplifted. Okay, this portion is uplifted. Not only this, but what we saw was the paleo banks of the channel over here. There is the paleo bank of the channel. Okay, there is another one here, and then you see. So we also saw the higher terraces, and this is lower terrace, one more, another. And if you remember, then in one of the lecture we were talking about the scarp height. Okay, so this was the section in normal faulting environment we were talking about, and I have shown this section where the topography of this was something like this. Okay, so you have this is the higher scarp H2, and this one was your H1. Okay. Now moving further, what we did was that of course this is one of the dangerous region, in the sense that if you carefully see the previous slide here, then you have two hydel powers sitting exactly on the fault. So if this breaks, okay, then you will have additional, or you can say the cascading hazard, which will result into the flooding, okay, in the low lying areas. Now coming to this part where we did the trenching, I'll just try to explain that how we identified different units and all that, and how and what basis we did. Of course, based on the satellite data interpretation, we identified the site. Went there, did detailed mapping. Okay, so this is the frontal part ground photograph, and along with the detailed mapping, we also did geophysical investigations in this region. Okay, the scarp is quite high, so you can have the comparison between this photograph and the digital elevation model. This is been represented by this hill. Okay, so this is the hill here. You have a Shivalix, and then further this topography which you see over here is this one. Okay, so this is the topography which you see. This is the first scarp we have and field, and then you have the second one here, which has been shown here. Okay, so we, as I told, that we did couple of trenches in this area, and now we have very detailed paleoseismic data from this portion of the Himalayan frontal part. Okay, and as I told, that we also did topographic extracted the topographic profiles, which clearly suggested us that as you move from A dash, okay, that is the profile over here, which is starting from the Shivalix right up to the endogangetic plane, crossing this structure. Okay, crossing the structure. So what we found was, in as we move towards along the strike, then the elevation of the scarp reduces. Okay, so it becomes almost near to flat A in this area. Okay. So this is what we do, that the gradual reduction in height of the scarp is attributed to lateral propagation of faults, okay, and growth of associated folds towards north. Okay. So this was an important finding which also helped us in understanding the direction of the propagation, and we were able to prove the overall process. Okay. So we also saw and that there is a back thrust over here. Okay, and we did some studies in the back thrust area. Okay, and also we were able to find this is a topographic profile, and then GPR profile we took, and this was the trench. Okay, so we were able to see the warping here, but we were not able to go up to the fault. Okay, because fault is sitting deeper in this area, or maybe it is very low angle. Okay, so with this detail mapping, again, as I told that we uh, tried that, okay, let us see if we are missing any event. So we did again a very detailed investigation in this region, and then we opened up the trench uh, along this second fault, okay, which I was showing, and then we did detailed mapping of the surfaces, and then saw that surfaces are also displaced. The older surfaces have been displaced much higher as compared to the younger one, and we tried to uh, restrict ourselves on the younger surface, because that will give us the latest event and the penultimate event in that region. Okay. As we have already discussed this, that we also did 3D mapping of using GPR to understand that how the geometry of the fault varies within a very short distance. Okay, so distance here is hardly 8 meters in terms of the length along the strike of the fault, and then we were able to see that there was some change in the geometry of the fault also. This was very clear profile which we got, and we were able to put the trench which has been shown here, okay, with the dash box. Okay, so this is the trench location you have, and then fault traces are been marked by the arrows here. So this was our first preliminary interpretation, and what we identified from this, because we were able to go almost like 4 to 6 meters deeper with the GPR profile, and we saw that there was another fault which is coming over here, and then it has been taken up by the newer fault like this. Okay, so this was the area which we opened, and what we saw in the trench was exactly same what we were able to observe in the GPR profile. Now in this we identify different litho units, as I told, and it is not necessary that you will be able to see similar units on either side of the fault. But we were fortunate enough that we were able to pick up the base of unit or base of unit B, which was marked by the gravel unit. Okay, so we were able to pick up this, and that helped us in having the knowing the maximum displacement, which was because of the multiple events. Okay, so we accordingly we picked up the samples, charcoal samples, as well as the samples, sediment samples for OSL dating we took, okay, from different units. And this different units, you can say that we learned in the beginning that you use color, then texture, and then grain size, okay, contacts. That helps you in identifying the different units, and you can clearly make out that there is a reddish soil over here which marks your unit B, and then further up then you have something like this. Okay, I'm roughly putting here, and then you have an unit over here. Okay, so that is your C. So this was your A, which was clearly marked on the either side of the fault. Okay, and then this portion is your fault plane. Okay, which goes further like this. Okay. And also we were able to see the shear fabric and all that in this. And this is the capping unit you have, which has been marked by green over here. Okay. So this is the capping unit. Okay. Now, based on the, so here also another one, trench close to the trench 1 which we did, we were able to see a clear cut deformation over here and termination of the gravel. Okay. And this is the fault goes over here. But further we were able to see that this reddish unit is riding over the blackish one, okay, which has been shown here. So fault extend further in the softer or finer deposits, and we, based on the ages which we found through OSL and the carbon 14, we were able to reconstruct and the deformation pattern as I was discussing in the previous lecture. Okay. That how we do the retro deformation. So, we reconstruct the overall scenario, that when was which was the event horizon, the horizon which remains exposed to the surface before the earthquake is termed as the event horizon. So, that event horizons, and based on that how many events have taken place and what was what which layers got deposited during the after the events, that also we try to see that. So, at least we say that we had 3 events from this trench. Okay. And based on compiling other trenches from the nearby area where we did, okay, what we found was that there was comparatively a much larger interval between the event 1 and event 2. When we compare the interval between the event 2 and event 3, and then we have done that analysis. Okay. So, we say that the penultimate event was around 1500 AD, which can be bracketed between 1450 and 1650, and the recent event was around 1800. Okay. So, this is how we try to identify the events and correlate our trench data with the other trench data also. Okay. So, with this I will stop here, and then we will continue with, we will come up with the new topic, okay, in the coming lecture. Thank you so much. Namaskar.